Good morning, everyone. How's our night? So we are coming by this time since the night was it short or it was not night first? Okay, well, how are we all doing now?
Thank God.
Really good. Offer. Okay. So do we have anybody that has finished? We're expecting some people to join the league of people that finish implementing GKR. Do we have any new person? Yeah? By the end of the day. Okay. Okay, so the goal today is to review KZG and Multilinear KZG. Right. So it's just going to be a quick one. Because I'm sure we all understand it, right? Right? The way people are looking at me like KZG Multilinear KZG. Okay, so let's review it. Then we'll probably do like is there a need for a design session for KZG, for Multilinear KZG? Is there a need? Not if people are badass already. Okay. So let's just review KZG. Let's start with KZG, then we go to Multilinear KZG. That's fine, right? So, separate GKR. Okay, KZG.
No, actually, let me present mine. Yeah, let me present mine so that you tell me where it's No problem, let me present mine for you. Yeah, it makes sense.
When it's after when we give the opportunity for somebody to present, it's after like we expect everybody to have gotten it. You get. So that is when we now like ask for somebody to come and present. You get. So the idea of presenting is just to share ideas, but everybody should get it first. You get before that. So I'm going to be reviewing KZG and Multilinear KZG, and then maybe a brief design session. Okay, so when we talk of KZG, KZG majorly works with univariate polynomials, right? Okay. And then we have different variants of KZG, like the multilinear KZG. So everything is just based on polynomial equality.
That would be classical concept.
Yeah, the concept, not the lemma, right? Okay, so
Sorry for that. There's something we want to say about it. Something about probabilistic something testing. What is like even remember the
I
probabilistic
remember.
polynomial testing or something like that.
So normally, in order to check if two polynomials are the same, they need to agree at deep is it deep points, right? But we want to be able to check that two polynomials are the same without necessarily checking at deep points. Yes, we just want to be able to check at one point to be sure that those two polynomials are the same. Yeah. Now this is just the call. But I'm recording. Am I recording? Okay, here I disconnected. So we want to what's going on? Thank God you said it though.
It was not recording.
No, it's recording, but the screen is not sharing. Okay, so we want to be able to check that two polynomials are equal. Let's say f of x and f prime of x, right? We want to be able to, we want to be sure that these two polynomials are equal without checking it at d point, right? And one way we can verify that is by checking it at a random point, where the random point we're checking it at is say randomly selected, right? So if the two polynomials agree at that random point, then with a great probability they are both the same polynomials.
But then the sample space which from which you're picking the random point has to be large enough.
Yeah, it has to be large.
Accounts for the high probability of saying that they are equal.
Yes. So if the polynomial is of degree d, if the polynomial is of degree d and the size of the field is basically the order of the field, right? Then the probability is yeah. D over f, right? So we either need a big field size, right? We don't need the size of the field to be very big, or we need the degree of the polynomial to be very small, right? So we either need the size of the field to be very big or the degree of the polynomial to be very small. And in most cases, the degree of the polynomial is the degree of the polynomial can get up to like 2 to the 20, right? So that's why in most protocols we work with fields of size um, say 2 to the 256, right? In order to have a big field size to ensure the security of the protocol. Does that make sense? Okay. So let's look at KZG, right? Say we have a polynomial f of x, right? If we evaluate this polynomial at a point x, we get v. If v is 0, that means the x is a root, right? But if v is not 0, that means x is not a root. But if we subtract v from the polynomial, that automatically makes x a root of this new polynomial we will get, right? Okay. And we know that, okay, let's use a, right? That automatically makes a root. So that means that if we divide f of a minus v by x minus a, we are going to get a quotient, yes, plus a remainder, right, where the remainder will be 0. Right? Okay. So if r of x is 0, basically our equation basically collapses to this. Yeah. And based on KZG, we can think of this right. Okay. It's f of x, right? So I can remember, like, if we have f of x, we are talking of a polynomial, right? If we have f of a, we're basically saying evaluate that polynomial at a, and we're going to get a field element. So based on these facts, our q here is our proof polynomial, right? This is our factor, right? And this is the new polynomial we get, basically. Right? And so basically with this equation we can now, or this is basically what the verifier checks, right? With respect to KZG, where the prover is responsible for generating the proof. And the prover gets the proof by evaluating the proof polynomial at tau, right? Of which the prover must have originally committed to the polynomial by
So this is what the verifier is for. But both x's are going to be
they'll be replaced, yes, with tau. So let me just,
but ideally the verifier does not have the polynomial.
yeah. So that's f of tau, which is the commitment, right?
Yeah.
Minus v, which is the said evaluation of the polynomial at a. We get q of tau, which is the proof, right? Times tau minus a. Am I missing anything? Okay. So basically in KZG, in order to be able to evaluate the polynomial, in KZG we majorly think of the polynomial and the univariate polynomial and the coefficient form, right? Where we have, for example, if we want to represent a polynomial x, I say x squared plus 2x plus 3, right? We are going to represent it like x to 3 to 1, right? Where the index depicts the power of x. We're all together, right? So this is basically how we think of the polynomial, and we want to evaluate it at a point. So this same polynomial, if we multiply it, or if we do a dot product with it, and let x to the 0, x to the 1, x to the 2, we're basically going to get 3 to the x to the 0, 3 to the x to the 1, right? Sorry, 2, and 1 to the x to the 2, right? Which we can basically think of as the original polynomial. And when we add all these values, we get the evaluation of the polynomial at x. We agree, right? I know all of us understand all this, right? But we're just doing a walkthrough. So we're going to make it, we're just going to walk through, right? Just so that we refresh our minds. Okay, so we have a way of getting the evaluation of the polynomial by doing a dot product of the coefficients of the polynomial and the powers of tau, right? Well, in KZG, we don't want anybody to know the tau, right? We don't want anybody to know the point that we are committing to the polynomial at, the point we are evaluating the polynomial at. And in order to hide that fact, we use an elliptic curve to encrypt all the all the powers of tau, right? So instead of us having like x to the 0, x to the 1, x to the 2, we encrypt them. You can use G1 or G2, right? X to the 0, x to the 1, x to the 2, up to x to the n, right? Where n is the degree of the polynomial, right? And we know based on the law of indices that g to the a, right, times b is g to the ab, right? Okay, so with this, when we do a dot product between our coefficients and our encrypted powers of tau, we get g to the x to the 0, 3, right? Right, which is basically still equal to right, and when we sum them up, we basically get g to the 3 plus 2x, which is the encrypted form of our polynomial. Right? So normally this will be done with tau, right? Where this is our powers of tau gotten from the trusted setup ceremony. Right. Right? Okay.
Yep.
And also, when the prover generates the quotient polynomial, the prover is also expected to evaluate it at tau, right? Evaluating it at tau is basically still doing a dot product with the powers of tau, right? So with that, basically the prover is able to generate this f of tau, which is our commitment, which is the evaluation of the polynomial, right? And okay, in order to get v, since the prover knows the polynomial already, right, the verifier tells the prover, okay, open the polynomial at this point, right, at a. The prover evaluates the polynomial normally, like he would, because he knows the polynomial, and he gets v, right? And then in order for him to get the proof polynomial, the prover divides, right? F of x minus v over x minus a. To get the quotient polynomial. If the prover is honest with v, after doing this division, there will be a remainder, right? But if the prover is honest, there will be no remainder. If the prover is dishonest, there will be a remainder. If the prover is honest, there will be no remainder, right? And then the prover will be able to generate Q of X, which is the proof polynomial, and then evaluate it at tau to get the commitment. Right? So he sends the proof to the verifier, right? And then based on this equation, f of tau minus b, q of tau minus a. Based on this equation, the verifier either accepts or rejects. Right? Okay. So where this is our commitment, in say G1, right? This is our evaluation point, right? The evaluation result, right? In G1 too. All this we multiply it by 1, right? Where this one is a G2 element. And then this is our proof. Our proof in G1. And we're multiplying it to this is our tau in G2. And A here is the point the verifier wants to evaluate at. In G2, right?
Yeah.
Okay. So I think like all of us are conversant with this, and I think it's boring us. Like the way we look like we're bored.
No, we haven't.
Okay. I'm thinking we should just go directly into like design session.
No. Which was this for Univision?
Okay, for univariate. Okay. So let's look into the trust set setup for univariate. Okay, so when we have the trust set setup, right? What is the essence of the trust set setup? The essence of the trust set setup is to enable us to generate the powers of tau, right?
Yeah.
The powers of tau, but the major thing is what we're trying to generate is tau itself, right? So we're trying to get tau in a way that nobody can know what tau is, but the prover and the verifier, right? And first of all, let's outline which law of indices we use or take advantage of. It's basically the law that G to the A times B, right, is equal to G to the AB. So
What about the one of if you're adding the basis, if you're multiplying the basis, you're adding the power.
Okay, so that's g to the a, that's the second law, right? Times g to the b. That's if it's a okay, g to the a times g to the b, right? And it should give us g to the a plus b, right?
Eh? No, this is where it's confusing me. You say G to the A times G to the B is equal to G to the A plus B. Yes. Okay, we're assuming the two G's are in the same group.
Yeah, okay, let's yes.
But if they're in different groups,
Yeah, if they are in different, like
If there are different groups, that way we do the
Bilinear
pair.
pair.
okay, that's fair. Well, I wouldn't know if the multiplication is supposed to be plus instead.
say it should be plus.
I don't know.
If it's plus, then this is not the law of physics.
Yes, I agree. But the generator, let's say they
Nice. Huh? Yes, that's like
yeah.
a, right? Okay. And same thing with b, right? So this is actually how it is, because when we have a group G1, we can't do multiplication, right? We can only add an element to itself multiple times.
Okay.
And when we say a scalar or G1, we are just saying multiply G1 by itself. Or we are just saying add G1 to itself a number of times. Right? So a times G1 is G1 plus G1 plus G1 plus blah blah up to yeah.
Do you want again? Just put
Okay, let's say 1 2, right?
That's confusing now.
No, this will be wrong, right?
C1.
Yeah,
just
because it's still the
do
same
one. And put
up to 8 times, but we get the jack. So we're just adding G1 to itself 8 times.
Okay. Okay, let's say we had A plus B.
A-
Then
Not like in the scalar.
yeah, just normal A plus B.
Okay.
Then when we include A plus B.
I want to encrypt A plus B. We can encrypt, we can add A plus B to get C,
Yes.
right? And then we can encrypt C.
C. What if I don't know A and I don't know B?
So this will still be equal to us encrypting A, which is A, right? And then okay, since we are using this notation, right, we are going to add it with B, right?
Okay.
So we encrypt A, we encrypt B, right? And then we add the two group elements.
Okay. So, but how does this translate to G1 raised to the power A plus B? Because what we know as G1 raised to the power A plus B is A G1 raised to the power A times G1 raised to the power B.
Yes. So, like, basically, we can still think of this as G1 because we're adding it to itself a number of times, right? right? So now we're thinking of it in terms of the generator, right? And then for B, you can think of it as G1 to the B,
Yes.
right?
Mm-hmm.
So now these two are their points,
Yes.
right? So you can't multiply 2 points. If you want to multiply 2 points, you use bilinear pairing.
Yeah, but we multiply 2.4.
That's because we are thinking about it in terms of the generator, right? This is a law of indices.
My brain is catching, but just.
I don't think it's technically multiplication, like just find it like that.
Yeah. So right. If we want to think of, like, I think it's best to look at it this way if you want to think of it as an addition. But then this way, where you want to think about it as a multiplication.
This now brings a open a whole can of worms. It was just now when I was saying we should put works there. They saying no, it was multiplication. School of. This here. No, like here. So you know say G1 is for A plus G1 is for B is equals to G is for A plus B.
Yeah.
Right? Here right now we've done, let's say, multiplication in the same generator point, right? The same generator we've done them. So but now what is the difference between that one and saying G1 is for A plus G1 is for B is equals to G is for A plus B? Because that's like what we translated here.
Which one? This?
Yes, that one, like, what we're seeing now is like that up one and that down one at the same time. No, like this, I mean, like, it's different things.
This one?
This A dot
Okay.
G1 plus B dot G1. We're seeing it equals to G1 to the power A dot G1 to the power B.
You know, like, when we have when we are dealing with points, elliptic curve points, if we want to multiply 2 points, we use bilinear pairing, right? Because these are 2 points, like xy, right? Can be 2 points, right? Like, but say these 2 points are on the same curve, just based on this example. Okay. But when we're talking about a point, like, it has xy coordinates, right? Okay. So if we multiply a point by a scalar, we're basically saying add that point to itself, that scalar number of times, right? So that's basically what we're doing here, right? If it's an additive group, you can think of it like this, right?
Okay.
If it's a multiplicative group, you can think of it like this, like the generator to itself,
Okay.
right?
Okay, so you're saying the first one only works for additive groups.
Yeah. The notation
The notation is for additive.
for additive groups,
Why
yes,
the bottom one is for multiplicative.
for multiplicative groups.
So what's the property of an additive group? What's the property of multiplicative? Why are they different?
They are not different per se, right? So, like,
Sorry, it's
we know.
just that, sorry, you are using a scalar to multiply the points, which is just like you are scaling it. But here, you are using a point to multiply a point.
Or you're adding a point to itself.
Eh?
See, here, right, you're using a scalar to multiply a point,
Yes.
right? Here, you're adding a point to itself.
To itself.
Yes.
But we said using a scalar to multiply a point is equal to adding a point to itself, that scalar number of times.
Yes. So it's technically, or you can think of it as the same thing, right? But it depends on the group,
It depends on the group.
Or
yes,
the operation of it.
on the operation of the group.
Okay. So what we're saying now basic is that A times G1 is not equals to G1 to the power A.
A times G1. It is.
It is. If
Yeah.
it is, that means the top and the bottom are not equal then. That is, what I mean is A dot G1 plus A dot G1 plus B dot G1 is not equals to G1 to the power A times G1 to the power B.
I feel the confusion is the operation.
Yes, the
If,
operation.
yeah, the point is that if our group, the operation defined on our group is addition, if this one is correct, if it's multiplication that is the operation in the group, the other one is correct. So it is equivalent, kind of, depending on the
That means it's different groups.
kind of, yes.
That means if it's different groups, that
Okay,
means
yeah.
it's not correct. That means these two are not equal.
It's
This
just
is
what
different
operation
groups.
is.
Yeah.
What operation do you want to?
What operation? What is the operation of the group?
The operation of the group. So if we have a group, you can only perform that operation with that group.
Yeah,
No
it's
other
only
operation.
one
Only one operation. If it's a ring now, it's two operations. Addition and multiplication is possible in a ring. That is a field.
Okay.
Technically not.
On a ring,
A ring.
yeah,
A ring is a subset, right,
of what?
of a field. Are you saying a field or a group now?
A field is a subset of a ring.
No. If it is bigger than
A field is a commutative ring.
you can't
With
say
identity.
No.
Yes.
A ring is a subset. A ring,
Okay.
not all elements in a ring has an inverse, right? But in a field, all elements have
Which
a
one is bigger, a
multiplicative
ring or a
inverse.
field?
A field is bigger.
But what I'm saying, what my thought is that in a ring, is not all the elements there that are commutative. Maybe a field is a ring with identity, with a commutative ring with identity, right?
A field.
an inverse.
Yeah, if identity exists, there is inverse. Yes, ma'am.
Mhm.
If there is inverse. Without identity, there can't be inverse. Yes.
So, for a ring, not all elements in the ring has a
Multiplicative
multiplicative inverse, right?
inverse. Yes.
But for a field, all elements in a field have a multiplicative inverse.
I think I get it. So all fields are ring, but not all ring are field.
Yeah, but not all rings are fields.
Okay.
Yeah. That makes sense.
Yeah. So now we are talking about group. So a group is only one operation
Just one operation.
that is there. So I feel that the reason why addition is possible there is because the group is defined. The binary operation of that group is addition, while the other one, the binary operation there is multiplication.
Yeah. So
And there are that makes them two different groups, or the same group with different operations.
hike. You can think of it that way, right? Same group with different operations, or different groups because of their operations,
Yeah.
right? You get so when we are talking about, like, when we have a group, right, it has an operation. That operation may be addition. If it's addition, it's an additive group, right? if it's a multiplication, if the operation of that group is a multiplication, it's a multiplicative group,
So,
right? And basically, like each group um, can have a generator, right? In the case of the additive group, if we have the generator, in order to get other elements in the group, we add the generator to itself, right? So we add the generator to itself until we get other elements of the group, right? If it's a multiplicative group, we multiply the generator by itself. Yes.
Okay,
Cool.
so that means that with elliptic curve, we are always working with additive groups,
Yeah, working with additive groups.
not multiplicative groups.
Yeah, not multiplicative groups.
Okay, now that narrows it down a bit, because you know when you were saying if you want to do okay, it makes sense. If you want to do multiplication on the group, we have to like no, not like we draw it.
That's one to multiply two groups.
No, not two groups.
If you want to add,
Add group, not to multiply.
Like if you have the generator, right, and then you want to multiply it with scalar. in this
You're adding
place.
it.
then you're
Yeah,
adding
you
it
are
to
adding
itself.
You're adding it to itself. That
Yeah.
scalar number of times.
Yeah.
So I was talking about drawing it on the curve. Like show us them. So that's for that one now. So now because we are always
Something like this.
yes, exactly. So now because we are always adding it to itself, we are not multiplying it by itself. That's why we are always using additive roots in elliptic curves.
Yes.
Okay. Fine. We should not be using multiplication in the first place here.
Actually.
That's the way to represent.
We can't even use it here at all because if we're using it, it's for multiplicative groups and we're working with only additive groups.
So
Going for it.
the thing is like
What is the elliptic curve? What is it defined on? Is it not a fluid?
the elliptic curve.
Yes.
Is it the base field you're talking about now, or
So the A and B are the base scalar field, and the elliptic curve itself is base field.
No, if you guys have got it from the field,
you know we have the base field and the scalar field.
Yeah.
When we have an elliptic curve is defined by a polynomial,
Okay.
right? X, yes,
Why is it?
s cubed, right, plus ax plus b, right? This a and b,
Ah, scalar field.
no, these are the base fields. Like a and b come from the base field, right? A and b come from the base field. Then we have the scalar field. The scalar field is basically the field that defines the order of points on the elliptic curve, right? So let's say we may pick 0, right? A equal to 0, b equal to 4. Right, this will give us an elliptic curve plus 4, right? And based on this elliptic curve equation, this defines a curve, right? This polynomial defines a curve, right? On that curve, there are infinitely many number of points, right?
Yeah.
But when we are working with in cryptography, we work mod a certain prime,
to cap it.
yeah, to cap it. So when we have a certain prime we are working with now, that means basically we are not talking about all the infinite number of points on this board. We are not talking about specific set of points up to that order, but that still obey the properties of a group, right?
So in a nutshell, elliptical polynomial is defined on a group, not field.
This elliptical polynomial, is it this one you're talking about?
The general polynomial is y s cubed plus ax plus b.
Yeah.
So where is the domain gotten from? Is it a group or a field?
A and B here is gotten from a field.
Like
That is the
whole-
base
The
field.
whole addition and everything, the whole polynomial.
Okay, the polynomial.
Can we call it a field, a polynomial field or a polynomial group?
A field.
The entire polynomial is a field.
Yeah.
If that is the case, you can perform both operations with it. You can perform both addition and multiplication.
When we pick an elliptic curve, we are now defining points on this curve that need to satisfy the group property.
So group property.
Yes.
So it will reduce it to be a group.
Yes.
It's like you have a group, you have a field, and out of that field, you are using a group. So the group, the field contains the group.
Thank you. Is it?
Okay.
So
Okay.
what I want that G dot that G1A dot G1B is not the dot there is not basically multiplication. That will just be the elliptical operation.
Yeah.
Then
So it's
so
the
not
operation
like
of the
the
elliptic curve.
then, and since we know that the elliptic curve is basically like addition, that is there, that's where we are. So since we have the basis to be the same, we just like add, since we are, it's just basically adding G to itself number of times. So that's why we just take the B to the top, so it does be A plus B. So if we have G dot G operator, G raised power of A operator, G B operator, G C and all of that, it does be G to A plus B plus
Why is
C.
no minus?
Yeah?
Why is no minus?
That's just a way of representing an operation in cryptography.
No, like-
Mostly used dot.
No, there is dots, right?
Okay, why is it not minus?
Why is no minus? There is not up.
Elliptic curve, you just
That
say
is
elliptic
up,
curve is an addition now.
Yeah, sure, it's an addition, right? Fine, but we moved from G1 to A dot G1 raised to power B to G1 raised to power A plus B. That way it was. So I'm like, why is no now G1 raised to power A minus B?
Is the elliptic curve is not, it's an addition, this statement, an addition,
No, addition
Oh,
is
yeah.
different
Where
from
exactly?
multiplication.
you're not getting it. We are saying that that dot there is not multiplication. That dot is just signifying the operation of the group.
Okay, so my question now is, how does that dot there help signify the operation of the power when you add them together?
He just told you that in the elliptic curve we only have one operator, which is addition. So if the only operation,
No.
that's
Ye-
what he said now.
Yes, but now we're doing if we're doing multiplication there, which is dots, right?
Okay. We are not doing multiplication. We are using dot to represent the operation of the elliptic curve. It's not multiplication.
Okay, so what you're saying is, even if there is
Oh, you
division
can
there,
just do any sign. There is just anything. You can use anything to. It's just a representation of this an
Right.
operation here.
so let's say there's an operation there. So what we're saying is, anytime the operation is reduced or is powers are by law of indices or whatever, and they are joined together, it always evaluates to an addition of the
Yes. It's an addition. So if you wanted to do a subtract a negation, you can negate b.
And to go to negation.
Yeah, you can negate b, and then you do the add
So-
the
so-
two group points.
Mm.
Like let's say minus
So
a.
that means that if we are saying it like that now, that means that G1 plus G1 AG1 plus BG1 is equals to
G1 raised to power of A plus B.
G1 raised to the power of A plus B. That is my point. That's what I want to say too.
Or in an additive group, you can think of it as like this is AB.
Time that you see that is the decision I'm trying to make now. So what you are now saying is that this A dot G1 plus B dot G1 is not equals to G1 raised to power AB. Because
That-
this is an
No.
additive.
Because this is an additive
Exactly.
group.
That is exactly my point. Because it is additional, we can't just say power. Because that would be for a multiplicative group.
No, okay, I think what is this AB now that is happening here. You know that one we are doing dot product dot this thing multiplication between two. That's why we are having that stuff in bracket B. So you now have G raised to AB. It's not plus in that sense.
No, we're not talking about that one, Sha. I know the one you're talking about, that we have to do G A then to power B, right? And it's not what I'm talking about, Sha. But this is
I think the thing is it's representation. So this A dot G1 plus B dot G1 can also be represented as G1 raised to power of A dot G1 raised to power of B, and can also be represented as G1 raised to power of A plus B.
Francis, that was not what we were talking about.
Right. So, but this makes sense, right?
Yeah, this makes
And-
absolute sense.
And it's clear that an elliptic curve, or basically a group, has one operation.
Yes. One operation.
So depending on the operation, right, that operation will determine what you can do to points in the group. If it's an addition operation, that means you can add 2 points in the group, right? If it's a multiplication operation, that means you can
Like
multiply 2 points in the group, right?
Yes.
So that would determine like how, for example, if you have a generator, say it goes back to the generator, A times G1, which is a scalar multiplication of A, and G1, which is the generator, means like adding G1 to itself, like multiple times, right? And B times G1 is the same thing, right? If it's a multiplicative group, right, and right, okay, so I think I get you. So if I get you right, what you're trying to say is A G1 plus that what we should have represented it as was, right, and G1 A
Yeah, and the two are not the same thing.
that's because they are different
Different
groups.
Yes, that's my point. So the question is, which one are we using?
because they are different groups.
Yes.
Okay.
So which one?
But
are we
this
using?
is an additive group and this is a multiplicative group.
Okay, so that means if we are doing this for elliptic curve, we are not supposed to be using the second one, the one at the bottom.
It's a notation something.
You know, in the last class, you said that this AB dot G1, right?
Yeah.
It can also be represented as G1 raised to of A plus B. So when you said it, it's what it signifies like is just another way of representation. But now you're saying that the first one is only that way because the operator is an addition, and the second one is that way because the operator is a multiplication. But you know, while you were explaining this stuff now, you represented it with the second one, and we are talking about elliptic curve, which the operator is always an addition. So it's kind of
Yeah.
confusing.
So what I'm saying is that this, like, we have A times G1, right? Which is a scalar multiplication, right? And we can still think of this guy as adding G1 to itself a number of times, right? We can still think of it as it's a notation something, G to the A.
That's what I'm saying. So
Right.
that means this can also be represented as G to the A.
Sorry.
Yes.
But if you say that means that's adding G1 to itself, not multiplying G1 to itself, is it fine to represent that equates to G1 is power A? Or if you're adding G1 to itself, it's not the same as multiplying G1 to itself. Like if you multiply G1 to itself, then to that power, that power becomes notative, like it becomes like 2 times 2 times 2 is 2 is power 3 because there are 2 3. So that's multiplying 2 to itself 3 times 2 is power 3. But if you say 2 plus 2 plus 2 is not like 2 is power 3. So like except probably maybe the elliptic curve just works. Maybe it takes it differently also.
Okay. Okay.
So actually, it's now there are two different things now. I just confirmed something. The way of representing generator is the second one.
That's G is from A.
Yes, G is pi, A. So on the elliptic of, if we are moving from one point to the other, we represent it the first way.
This one.
Yes.
But the way of, you say the way of representing the generator.
Yes.
Okay, is this way.
With this way.
So your material, can you share it?
I asked you. So
But it's okay now.
Okay. So
Sure.
I don't know.
Yes.
I don't know what I'm doing.
okay, so let's look at multilinear KZG. Hmm? Okay. So basically, like, multilinear KZG is an extension of the, you can think of it as an extension of the univariate, right? All right. So f of ABC minus v is equal to the summation right? So we still have the concept of our commitments. We still have the concept of our evaluation proof. We still have the concept of our evaluation results, right? We also still have the concept of our proof and our factors. Well, now since we have like multiple variables, we are going to be dividing, or we are going to be adding like them up, right? Our proof times the factor, right? So basically another different thing about the multilinear KZG is, but in our case we are working with the evaluations of the polynomial, right? So we know how the evaluations of the polynomial, we know that the evaluation of the polynomial, which is say y, right, times its Lagrange basis, is going to give us like the summation of this, right, yi times the Lagrange basis of I is going to give us the polynomial evaluation, right? So in the univariate case, our powers of tau was the like powers of the point we want to evaluate at, right? But then in the multilinear case, since we are not working with powers basically, we have, or what we get back from our trusted set of ceremony is an encryption of the Lagrange basis, right? So we basically know how to get the Lagrange basis, right? In a situation where we have like 0, 0, 0, 1, 1, 0, 1, 1, we need to do like check 0, check 0, right? Let's say this is A and this is B. Then check 0, check 1, check 1, check 0, and check 1, check 1. So this is just like an example for two variables, right? But depending on the number of variables, this can span as long as, depending on the number of variables we are working with, right? So basically 2 to the number of variables, right? So and after we've gotten these values, we'll encrypt them, right, using our generator. We'll encrypt each of these values, right? After encrypting all these values, we can then do a dot product with the evaluations of the polynomial and encrypted Lagrange basis. In order to get our commitments. In order to get our commitment, right? And in order to get the proof, we divide the like we have the polynomial, right? We divide it consecutively by the different factors. Divide by the factor with respect to A, and we get a quotient and a remainder, right? Where our quotient is the quotient with respect to A, and then for the remainder, we'll need to divide again with respect to B, right? And the goal is that after we finish dividing by all the factors for all the variables, we are going to get 0 as our remainder, right? But if the prover lies, then he won't be getting 0 as a remainder, right? If he actually does that. But in most cases, if the prover is lying, that means technically did not even do that, right? But then with what the verifier has, with the information the verifier has, the verifier can verify if the prover was honest or not using this equation, right? Where we have this guy in G1, right? And we have times 1, which is in G2, right? And these are Q for each of the different variables, right? For each of the different variables, Q will be in G1, and then this would which would technically be tau at I. Let me just put it here. Tau at I minus xi, where xi is the point the verifier told the prover to open at, right? And it will be in G2. So when we do this multiplication, basically the proof times the corresponding factor evaluated at tau. Right? When we do this multiplication, we're going to get an element in the target group, right? And then we're going to sum them all up depending on the number of variables, right? And after summing them up, we are going to check if it's actually equal to the left hand side of the equation. If it's equal, the verifier accepts. If it's not, the verifier rejects, right? So like some people have been asking questions, especially like with respect to the proof polynomials. Right. You know, when we generate the quotient and the remainder, let's say for Q of A, right? When we generate the quotient, A won't be in the quotient again because we've taken out A, right? And A won't also be in the remainder, right? It's a good thing for us that A is not in the remainder because we'll continue further to divide, right? For A not being in the quotient, we know we're still expected to evaluate the quotient at tau of A. Sorry, at tau of BC, right? And we know basically that the Lagrange basis polynomials we got factors in both tau of A, tau of B, up to tau of N, right? Like tau of C up to tau of N. Like all those things have already been factored into the Lagrange basis we have. And if this guy is short by one variable, we can't technically do a dot product, right? So we basically have that blow up formula, right? So with that, we technically blow up this Q of A back to Q of A, B, C, right? By adding plus 0A, right? So enable the both of them to have the same number of elements so that we can do a dot product. Right. Okay. So, like um, if this was three variables, A, B, C, right? That would be 2 to the 3, which is like 8 evaluation points. After we've gotten our Q of A, our Q of A will be in BC, right? Which is 2 to the 2, right? Which is 4 evaluation points. Our Lagrange basis is made up of the encrypted values for tau, tau of A, tau of B, and tau of C,
Yeah.
which technically means that it contains
8
8 points, right? So we can't do a dot product with 4 points and 8 points, right?
So at what point are we doing that dot product?
When we want to evaluate Q of like all the Q polynomials, when we want to evaluate them at the corresponding tau, right?
So before we evaluate the cubes, we have to blow them up to ABC back,
Yeah, you need to blow it up to ABC, right?
and then evaluate it at one corresponding, partial evaluate it or full evaluate.
That will be a full evaluation, because in as much as this is 0A, it won't count. And in as much as this is 0A, you're blowing it up and you're adding 0A, right? So that technically takes out the factor of A in this. So you blow this back up to 8 so that you can do a dot product between the Q polynomial and the Lagrange basis. Is it making sense?
Yeah, it's a revelation. The only place I thought we were multiplying this and this was probably at the beginning time when we had the polynomial and the taus. I didn't realize we were.
This is the proof polynomial with respect to A.
Yeah.
To generate our proofs, we need to evaluate them at we need to evaluate the proofs at tau,
So
right?
does this mean that even for QC for QB, which is in terms of C, we are going to do the same thing, blow it up to ABC,
Yes,
like double it down like ABC, and then multiply it again by tau.
yes. So the further down we go, the more the blow up parts. Okay. So say we have a polynomial f of a, b, c, right? When, let's say we're told to evaluate at a, b, c, so we need to generate corresponding proofs, right? And in order to generate the proof, we need to generate the proof polynomial. It's then the proof polynomial that we are going to evaluate at tau to get the proof, right? In order to get the proof polynomial with respect to a, we divide f of a, b, c, right, by x minus a, right? And when we divide this, we get a new polynomial q with respect to a of bc, right? This polynomial, the number of evaluations of this polynomial was 2 to the 3, right? 3 variables, so which is 8, right? But this q polynomial is 2 variables, so that's 2 to the 2, which is 4, right? So our powers of tau in G1 was an array of, let's say, for three variables, 0, 0, 0, 0, 0, 1, 0, 1, 0, up to 1, 1, 1, right? It's factored in tau of A, tau of B, tau of C, right? Where this first one is 1 minus tau A times 1 minus tau B, 1 minus tau C, right? Okay. And also, like for this one, 1 minus tau A, 1 minus tau B, and tau C. Okay. And these values are encrypted, so we don't even know what the taus are, and they are just one single value. Yes, they are just one value. So, but the thing now is that these are Q of ABC. We want to evaluate it at tau of B and tau of C, right? But then our Q of ABC is actually four elements, and this array, which contains our corresponding taus, is made up of 8 elements, right? So if we knew tau, what we would have done is to use tau to evaluate, fully evaluate this. But we don't know tau, and tau is hidden in these guys. Tau is hidden in this guy, right? So one way we could do it to enable us to still do that dot product is by blowing this Q of A up. So we blow it up to be Q of A, B, C, right? Which will now be 2 to the 3, which will be 8 elements, right? But we blew it up by adding plus 0A, right? So this plus 0A will technically, like when we do the dot product of this guy that we've blown up by adding the 0A, and yes, so this is technically evaluating the polynomial Q of ABC at tau.
So wait, multiplying it like that is evaluating, is the same thing as evaluating.
The dot product.
Yeah, like the dot product, like that, like element wise multiplication.
And the summation. Yes.
Is okay, multiply and add.
Yeah. The same way you
Did for
generated
the-
your commitment.
Yeah.
So,
Right.
The blowing up is so that if you have the number of variables as the powers of tau.
Yes.
can you scroll up? Yeah, I think keep going. Yeah, just put it like here. That is your saying G1
Yeah.
no, jump down. Yeah, yes, down to okay, go to
Okay. Okay, so
Sorry, Frank. I wanted to ask, like, in GTR, we could only go up from the back, from the front, because it's B and C, and it's always going to be B and C.
what I can always, based on your implementation.
So I didn't do tensor, I didn't do block, I did tensor.
Okay.
But normally in GKR, if you want to block, because from the whole GKR equation, it's basically WBWC, WBWC, WBWC. There's no time where it's WT or something. Right? So you can only block either from the front, when you want to block A, and when you want to block B, or you can block from the back, when you want to block C. Now, in this scenario now, where it can be A, B, C, D. How would the blow up happen
Oh wow. Oh, you're always going to be blowing up from the front.
from the
Right.
front?
Yes, because when you divide
Yeah.
by
A goes out.
A goes off, so you blow it
Anytime
back
you
up.
want to do, you just blow up only
Yeah, you just blow up it for that particular round.
A. Yeah.
Then when you go to when you go to yeah, you get a
When you
remainder, right?
remove B and you're now left with C.
With C. So you add
You blow
B
up B and blow
and
up
A.
A.
Yes.
So that means you first blow up B first. Then the result you now blow up A.
Yeah.
So that area of this thing, what is it called again?
The Lagrange.
No, Lagrange basis, right?
Okay. So
How do you get to since we don't know that?
yeah. So the person initializing the trusted setup for now, right? You guys, what you guys will implement will be like you initialize the trusted setup, right? So the person initializing the trusted setup knows the tau he contributed, right? And he generates the Lagrange basis table, right? This table, right? And after generating the table in the clear,
Sorry, I was. How are they generating the table again with that?
in the trusted setup,
Yeah.
the person that initializes the trusted setup, he knows the values of tau that he will be adding, right? The tau for the different variables, right? So with those values, he calculates the Lagrange basis in the clear
Okay.
and then encrypts it.
Okay.
Okay,
Yeah.
so he knows the values of tau, he calculates it and he encrypts it, right? So for now, people should pause on contributing to the multilinear KZG trusted setup. You guys should just implement like initializing the trusted setup, which is generating the Lagrange basis,
Okay. For now.
yeah, and then encrypting it. We are not implementing like yes. Like say in when the person wants to initialize the trusted setup, you know the trusted setup is a different protocol on its own, right? So when the person wants to initialize the trusted setup, the person will pass in the person's values for tau, right?
No, I think
And
she
based on those values, you generate the Lagrange basis.
The person passing the value of tau, not just doesn't send the value of new value. Each person will see their own value of like the other values.
No, like in the trusted setup, the person passes in the values for tau. So yes,
So I think what she's what
or it depends on how you want to go about implementing. Yeah.
They can come with tau A, tau B, tau C, or if you have like polynomial theory, can they not come with the values of 0, 0, 0, valuation, tau A, tau B, tau C? Do you understand what I'm talking about?
Okay, yeah, I get you. So what you're trying to say is that
So they come with tau A, tau B, tau C.
why don't the person generate this table outside and then bring the table?
No, other parts like contribute to it, so why not do it outside?
You know, like say you want to make your library public, right, for people to use. You don't want people to stress themselves to start calculating, so you can help them do that, yeah, by having like say a function that generates the Lagrange basis. So the person just brings the person's values for tau, and you do the calculation for the person.
Okay. Then you get this one, but then you
Yeah,
get the analysis, then the other person can come, get the analysis, and then the other person.
for that person. Yeah. Yeah. But for now, like the contribute function, like there should be an initialize function for your trusted setup. So let's say we have the trusted setup. Right? There should be an initialize. There should be a contribute. Right? For this contribute, for now, you guys can pause on it. Right? But implement this initialize. Right?
So what does the initiality do?
For the initialize, you can decide to take in the polynomial, or you can decide to take in the degree of the polynomial.
Okay.
We don't really care what the polynomial is. What we care about is the degree or the number of variables, right? For the multilinear case, the number of variables. Right?
So the tau square.
Or is there any need for taking in the number of variables? There's no need, right? Yes. So you can just pass in tau A, like an array of taus. Right? Yes. So based on the length, we know the number of variables, right? We know that we are meant to return a vector of G1 elements.
Is it from this initialize function we are doing that, or there's another function we now use to do that, to generate that?
And the initialize function.
So you
And that's the G. You said we were not even the G that the London believe is our
Yeah, like this array of G1 elements is the Lagrange basis encrypted. So all these values, G1 to the for each of them.
these G's, how do we get them?
Okay. So how come? But does this make sense? That they're meant to return an array of G1 elements.
Yeah.
Makes sense, right? So in order to get the G's, right, we have Arcworks has this arc. Is it this arc? Is this arc, right? Arc EC.
EC.
Yes. So arc EC, that's the elliptic curve. Right. And inside this arc EC, they have the pairing traits.
Pairing straight.
They are pairing. So normally what you guys have been doing was F prime field, right? But now basically for the multilinear trusted setup, yeah, it should be right. So this is generic, right? You can call it anything. So you can call it F, you can call it P, yeah.
So how are we using the pairing of the number? It is mainly the elements in GT that have that pairing problem, right?
The elements in GT,
Yeah.
no.
Like,
Like, well, basically, like on this pairing, you can get G1 from it, you can get G2 from it, you can get your generator. You get, so everything is kind of like available on this guy. So you said something about GT being the only one to the pairing is a three-way stop, right? We need There are three people involved when we talk about pairings: G1, G2, GT, and it's not all groups that are pairing friendly or that support pairing.
That's by linear pairing.
Yes, by linear pairing. You get. So we need to be sure that the groups we are working with support pairing. Yeah. So in order to get the G1, this thing, you can do like P G1, right? Which is the G1 group on that pairing. The thing. So let's say if you're using BLS 12381, this will basically give you the G1 group for the BLS 12381 pairing friendly code.
So are we started in the lesson?
Yeah, what's that?
So quickly, the trusted setup.
Yeah.
The trusted setup, does it need to have a struct so the does it need to have a struct to keep track of something like
This question, like, you just tell me to write it for you.
That initiate function.
eyes one?
Sorry. Okay, the initiate function is what is it taking the tau? The tau are array of tau.
Yeah.
But we don't know tau now. How are we getting the array of tau?
If you don't know tau, how do you want to contribute
So you just get your tau.
your own tau?
This
So
is
you
for
know your
univariate.
own tau. No. It's
Just
multilinear.
a setup for univariate or multilinear.
No, for multilinear. So that's why it's an array of taus, right? If it was for univariate, just one tau is sufficient, right? But since it's multilinear, it's an
It's
array
just
of
for one
taus.
person.
Yes.
So this will give us a group.
Yeah, it will return the encrypted form of the Lagrange basis. So it calculates all this depending on the number of variables, right? And then it encrypts each of them and returns it.
Encryption of the
It's G1, right? You can decide to use G2. So G1 to the power of the corresponding. Yes.
Okay.
Yeah. So this array is basically elements in G1.
Alright.
Yeah. So, sorry, let me answer. So you asked like the trusted setup, right? If it needs to hold anything.
Yeah.
So it will depend on your implementation, right? So like when you guys were implementing Shamir, right? I said something about stateful and stateless, right? So it depends on the approach you want to take. If you want it to be stateful or if you want it to be stateless, right? Or in most cases, you would want a situation where you can instantiate the trusted setup and then you want other people to come and contribute to it, right? So if you want other people to come and contribute to that particular instance of the trusted setup, that means it needs to have a state, right, where it's keeping track of everything. Or it can still be stateless in the sense that it basically returns back the encrypted this thing. So in the stateless implementation, that means the function will need to take in the array of G1, which is for the previous person that contributed, and the new taus, right? don't know if it makes sense. Like in the stateless, right? Since you're not keeping track of anything in state, I am totally against this too, right? Because okay, let me just explain like how the stateless will look like. So for the stateless, you will need to take in the array of
Yeah.
okay. So in the stateless, we need to take in the G1 array of G1 elements, right? Hope everybody's following.
Yeah.
We need to take in the array of G1 elements, where this array of G1 elements is what the result of the previous person's contribution, right? And then we need to take in the taus for the new person that wants to contribute. If that's the first, okay, that's why you now have like initialize and contribute. So there's the contribute function. Yeah.
Technically, initialize, if you want to you know that this one could also be a initialize function. If it's that case, because we are passing in tau to create new G's, passing another tau again. Do you understand? I mean, for the state that
For the stateless.
like, they don't have to do. So, initialize also contributing, we're going to be for the first person.
Yeah, but like if we want to, that means this G1 array will basically be just maybe an array of only the generator, right?
No, I was talking about the stateless.
For the stateless.
The thing is, I think that you know that initialize that technically contributes was it is a contribute function.
Function.
Not like just the first person. But if you
For
go
the
to
first
stateless, if I get this information, I used to contribute
For the next person. Yeah. So yeah. So why I said like against it is because like you're not keeping track of it, so you need to get it from somebody, right? What if that person is dishonest, right? But normally trusted setup, this trusted setup, it doesn't just return this value. It also returns a proof that you contributed honestly.
Wait,
That's
it's
the
not
actual trusted setup.
okay. Actually,
You get the one they use in production. So you also need to return a proof that you contributed honestly, meaning that you were working with the powers of tau that the person that contributed before you they gave you, right? So somebody contributed before you. After the person's contribution, we had a new powers of tau, right? And now you're coming to contribute. So you need to prove that your contribution is working with the previous one, because people can be crazy, right? They can decide to leave your own and go like 5 instead, even possibly even go to the first person's initialization, right? So when you're contributing, you also need to generate a proof that you're actually contributing based on the last yes, the last contribution. Yeah. So that's usually like part of this thing. So normally at the end of the trusted setup ceremony, they verify all the proofs of everybody that contributed. You don't necessarily know them, but you have their proofs. The proofs are public. So you start from the first person and you verify that everybody that said they contributed actually contributed, and that their contribution was based on the previous person before them. Huh? I've I've not really looked into it. Yeah, I've not really looked into it.
Look into what?
Yeah, it improves for trusted sector contribution.
So can we say that the array of tiles, do we put them now in P field? Do we get them in the P field, or do we say they are in the F field? Since the trusted setup is mostly like about the P field, like it's about the generator and stuff like that. It's easier to kind of like take in the array of tiles in the P field so that you don't have to do some this thing.
If you're taking the array of tiles, the array of tiles will be field elements, right?
Field element.
Yeah. So they are normal field
That's from
elements
prime field.
from the prime field. So it's when you encrypt after generating your Lagrange basis. When you encrypt, then that's when you now get the G element. These are group elements, right? But these are scalars, basically from the scalar field of the elliptic curve, or just basically field elements, right? Okay, so we have the initialize, we have the contributes.
How is it when the contribute?
So that's what I said, that I'm just post on it. Then I also depends on how you want to go about your implementation, right? It can be stateful or stateless, but I would say go for stateful, right? Because like if it's stateful, it can always be on the blockchain, right? You can the trusted set of parameters can basically be, since it's stateful, can be in a public place that everybody knows, everybody can verify. Somebody cannot just go and change it, right?
Stateful, like stateful implementation, right?
Yes.
Means we have some states that we are storing.
So you're basically keeping track of
Okay,
the Lagrange, encrypted Lagrange basis. Yeah.
Just implementation detail.
Yeah, it's implementation details.
You want to make it stateless, but keep the encrypted, the current encrypted file somewhere else.
Yeah. So it's just implementation details.
So how do we? I know you said we should not implement the how's it called now? The contribute yet. But then, what if the first person comes with, say, an array of 3,000 elements, and the next person comes with an array of 5,000 elements? How do we check, or what are we supposed to? How are we supposed to undo something like that?
The protocol will, depending on the number of these things, right? Like depending on the number of elements in this array, you automatically know the number of variables, right? Which is log list, right? Of the length of this array. So when somebody comes with,
So meaning that it is technically the first array of term marks how many others can do.
yeah, basically like even in the univariate case, when you want to do a transfer setup, you have a particular polynomial in mind, right? So you may not have like a particular polynomial in mind, but you're keeping a bound on, you're putting a bound on the,
Number of variables.
yeah, both on the number of variables and in the univariate case, the degree of the polynomial. So that's basically what you use to instantiate. So we should have that in mind when instantiating the protocol.
But for multilinear, it's not limited. Like for multilinear, it's the same way. For univariate now, if the boundary or the degree is 10, you can still use the polynomial of degree 2 on those powers of power, correct? Yes, you can see the of the return those powers of power.
You just take the first this time.
Eh?
You just take the first three.
The first two, yes. So for one of for multilinear, for instance, if you look at the encrypted values of power, okay, wait, hold on. For multilinear, we just have to have the encrypted values of power. Then we always generate the encrypted Lagrange basis on our own.
For multilinear,
Yes.
no, you need to have the encrypted Lagrange basis. That's what this function returns, right? The encrypted Lagrange basis.
So it's not possible to have the encrypted tiles. They use the encrypted tiles to generate the encrypted Lagrange basis.
That will now mean you want to do a multiplication. That will be, let's say you have the encrypted tiles, which is g to the tau 1, g to the tau 2. And then you want to get 1 minus tau 1,
Okay.
right? And then you want to multiply it with 1 minus tau 2. Like, this multiplication here will be a bilinear.
Okay.
Yeah.
So that would mean that if you have a multilinear of if the tau is originated for a multilinear of 10 variables, right? But you want to use it for a multilinear of 2 variables, you have to block a polynomial for 10 variables.
Yeah, technically. But I'm sure there will be more efficient ways to pick the values in the array you need. Yeah. Because you know, like, the first element is always 0, 0, 0. Second
Yes.
element is always 0, 0, 1. Yes. So there should be like efficient ways to just pick the indexes you want. That will be, maybe if it's 2 variables, that will be all the places where you don't care about the places where C is.
Yes,
Right.
yes, where C is 0,
Yes.
1, don't
Yes. So you don't care. So you just pick the
A and B.
A and B. But A and B still in the same sequence of 0, 0, 0, 1, 1, 0, 1, 1. Yes.
Okay, that makes sense. So you just find that pattern and say it. I think it's very challenging.
Okay. So does it make sense? Does anybody have any questions?
So you said you were putting a bound on the number of variables and words for multilinear.
For multilinear, it's the number of variables.
Just number of
For
variables.
univariate, it's the degree. Okay. So with this, basically we can now evaluate our proof polynomial, right? So we blow up our proof polynomial, evaluate it at the Lagrange basis, or do a dot product between it and the Lagrange basis, right? So, we still need to do this tau minus a part, right? Where is that? Well, we know the tau minus a part I'm talking about. Yes, this part. Right. So also in the trusted set of this, we need to encrypt all the values of, like, all the taus. We need to encrypt them in G2. Right. So we are going to have an array, like it will also be part of what we are going to return in the trusted setup, right? An array of G2, like G1 and G2 elements, right? So where this one is just the different powers of tau in G2. So that's
Same power of time, but now computed in G2.
in G2. So we're not in G2, we're not getting the Lagrange basis, right? We're not generating the Lagrange basis in G2. We are just encrypting tau in G2, right? Okay. So
So in G1, then is it in for the total setup now? Is it right to keep track of the Lagrange basis or the G1 array?
I don't understand it.
We are trying to make it stateful. So now in the structs that we might be creating now, is it for that G1 once we receive the town, we'll first kind of like get the Lagrange basis, and then after that we now encrypt them. So do we keep track of this now? You say we are not oh, that means the two of them we are doing the same thing, like getting the Lagrange basis and then encrypting them, only that this one is being encrypted in G1 and this one is being encrypted in G2. Is that correct?
No, that's not correct. For G1, we generate the Lagrange basis
Yes.
and then we encrypt it.
Yes.
In G2, we don't need to generate the Lagrange basis, right?
Okay.
Because of how we structured this our formula, right? Because of how we structured this our formula,
Okay.
right? So if we wanted to actually, like, it's going to be a pain, like if we wanted to switch this, maybe make this G2,
Yeah.
make this G1, that
Yeah.
would now be a problem, right? But since this is G1 and this is G2, we don't need to generate the Lagrange basis
Okay.
in G2. We just need to encrypt the tiles. Just encrypt
Just
the tile
encrypt
in
the tiles.
G2, yes.
So if there are 3 arrays of tiles, you have 3 dimensions.
Yeah,
So I see 3 elements in the array tile. You should have 3 values.
in G2,
In
encrypt
G2.
it. So, is it making sense? So once we have the encrypted values of tau in G2, because of this, we can basically do that minus our xi or our respective ABC encrypted in G2, right? And we can do that subtraction, and then we can also do this multiplication using bilinear map, right? And then when we do the summation, it should be equal to this. Like the both sides of the equation should be equal. Okay. Does anybody have any question? Okay. In the absence of any question, so let's look at our multilinear KZG protocol, right? So we've looked at the trusted setup, right? And I'm sure everybody knows what to do for the trusted setup now, right? Yeah? Does everybody know what to do for the multilinear KZG trusted setup? We know, right? Just generate your Lagrange basis and encrypt it in G1, and also encrypt all your tiles in G2, right? You're going to return those two things. So now for the multilinear KZG, we know we want to have
that encryption. That's just using doing G to the power of that. What's this now using to where we're getting G from? What language?
okay.
Maybe at something. What is the
At E6.
Okay, that's where we get the G from. Not the pairing. I know you said pairing. We can find the pairing traits in that.
Yeah, so on that pairing trait, we have G1, we also have G2, right? So you can get like G1 and G2 on that pairing trait.
But I'm talking about the G, small G.
Small g,
Yeah.
like G1 will have its own generator,
Okay.
G2 will have its own generator, right? Then we also have like when you want to do the bilinear pairing, we also have pairing, right? Is it pairing or pairings?
Pairings.
Pairing, right? Okay. So where we now pass a G1 element and a G2 element, right?
When are we doing the pairing?
Yeah?
Which one is this pairing?
But this pairing is the bilinear pairing from arc FF, like from arc EC, right? You can have access to the pairing traits. This P is the pairing trait from arc EC. The pairing trait from arc EC. And on that pairing trait, there is G1 and G2, which are the G1 group and the G2 group, right? And then we have the generator. Each group has its own generator, right? And still on that pairing trait, we have the pairing function, which takes an element in G1 and an element in G2 and gives us an element in G2.
So, at what point are we putting this G1 and G2 together in the pairing list? Are we calling it at what point are we put together?
This is G1, right?
Yes.
And this is G2.
Okay.
So at this point,
Oh,
this is G1
okay.
and this
And
is
this is
G2.
Oh, I thought we were kind of like performing a kind of dot like more operation and that kind of thing. So you just pass. That means that you just pass this one as G1, then you pass that one. Then you just pass this one G1 G2, then you compare it to that one G1 G2. We don't have to concern ourselves with the dots that we have to do a kind of multiplication over the two sides.
Okay, let's see.
Like these dots now, for instance, now normally signifies that
Sorry, which dot?
Q1 dots.
Oh, this dot.
Yes, normally signifies that once you get your Q1 value and then you get your this right hand side value, you do a multiplication of both sides. So I'm now saying with the pairing now, doesn't mean we don't really have to concern ourselves with that. We can just pass, once we get our Q1, pass it as G1, and then once we get our T1 minus xi, we pass it as Z2.
Yes, because the pairing is multiplication of group points, right? So the pairing is the multiplication of group points. There's no other way you want to multiply G1 and G2. There's no other way. It has to be pairings, right? So when you now, like, when you have this point, you agree that Q1 is a point,
Yes.
right? A G1 point.
Yes.
And you agree that this guy
Will also be a point.
will also be a point,
Yes.
right?
G2
So-
point.
So once we have those 2 points, we just call the pairing function, right? Pairing and passing those points. Makes sense?
Yeah, and it's the verifier that is doing this one.
Yeah, it's a verifier that is on it. But you know, it's a running sum, right? Since it's multilinear KZG. In the univariate, we're just going to check if this is equal to f of tau minus v times 1, right? But in the multilinear case, we now need to do a summation. So
Yeah,
each
that's true.
each proof with its corresponding factor.
So we'll compound this first before comparing it to the left hand side.
That's what the equation says.
And but you are the one telling them what the equation says.
So I've said it now. I've said it, right? Well, it makes sense, right? Okay, so so for the multilinear case, sorry, does this part make sense?
Yeah.
Sure. Does it make sense?
Yes.
Does it?
It makes sense, but I don't know how to grab it.
You figure it out. But like theoretically, it makes sense.
Yeah, I understand.
Goodness. Favor. Does it make sense? Ike. Mitch. Jean. Frankie.
Super fun.
For those that have been following, let me direct my question. For those that have been following, does it make sense? Eh? Okay. Because there are people that have not been following and they don't care. Right. They've not been following and they don't care.
So, like, okay, let me not disorganize the regulation. Don't worry.
I can only laugh. Eh? I can only laugh now. It's a. I need to laugh now. You get. We are human beings. We need to. You get. It's important. Eh? No, definitely. Eh? No, the thing is like it happens. We don't. We don't know. We don't know if it will even happen. You get. So I cannot wake up one morning and you get. That was how the last one happened.
Are you for you?
What's that?
That was how it happened.
What's that?
So it depends. Like,
Like, you just talked class.
huh?
We know you
Okay.
everything.
No. No, like
Something that some people
it was like
understand and
a
they don't
day before that day.
Wow.
We just looked through what have been going on, like submission and everything, and it just happened, right? So the next one, they may be in class at that one, or just like,
So happen at once.
Okay.
and it can be now. Okay, so so nobody knows. Only God knows. Even me, I don't know.
See,
No,
this
honest.
Jesus thing. This Jesus reality.
Okay, so okay, sorry. We're talking about multilinear KZG, right? And I was like, does this make sense for those that were following, or for those that were paying attention, or for those that care to pay attention? Right. Okay. So multilinear KZG should have a commit function, right? For multilinear KZG. After getting your trusted set of parameters, you need to commit to a polynomial, right? So you should have a commit function, right? So what does the commit function do? So for your multilinear KZG, stateless, stateful, stateless, stateful, it depends on you, right? That one totally depends on you. Like the security of, like in as much as, okay, then it should actually be stateful.
It should be stateful.
Yeah, like your powers of tau, right? It depends. Let that one be design decision. You get.
So sorry. In we have trusted set of as a protocol. Like, is it going to be within that same vision, or are we calling a library on its own, or we're just like just
Or you can make it a library, like process setup. People, it's not just because of KZG or the process setup, right?
there are other things that we need to
Yeah, there are other things like structure setup.
But the choice set of process we're doing specifically for multilinear KZG.
Not specifically for multilinear
So
KZG,
like,
for multilinear polynomials.
okay, sorry, for multilinear. So where else can we apply the process setup apart from KZG?
apart from KZG, like Plonk, if it's Plonkish, like a Plonkish protocol, right? You still, they still do trusted setup though.
Can use the one we use for multilinear for this KZG for its plumb.
Univariate, when you're committing to a univariate polynomial, it's a polynomial, it doesn't care where you're using it. So it's a polynomial commitment. Where you're using it is not its business. It just enables you to commit to a polynomial.
Wait, for plumb, are we using the trusted setup or are we using KZG?
For Plum.
And
It depends on, like, you know, like Scroll.
okay,
Scroll uses Plum and KZG.
okay.
KZG for the polynomial commitment. Plonkish IOP. Like Plonkish arithmetization together with the Plonk protocol and then KZG.
Okay, so let's say for instance there was no KZG in school. Would they still do a trusted setup?
If there was no KZG in school, would they do a trusted setup? They can decide to, right? A trusted setup. Some protocols use the trusted setup to encrypt, let's say like Grot 16 now. I started going into I don't want to get you guys confused.
Just continue.
Okay.
Complete now. The anytime you see it, remember you complete it.
My question, sorry, I got it. Was that so as far as the protocol, are we calling trusted setup inside or it's going to be called outside? It's just that you're passing the powers of the results that trusted setup is into the protocol. Or is it part of the protocol that you're initiating trusted setup?
Is it the multilinear KZG? Like, you can decide to initialize your trusted setup in the multilinear KZG, but you should have a trusted setup. Yeah.
So I want to know, is it part of the protocol? Because something like KZG and Multilinear KZG, evaluating the circuit to get the sums is not part of the protocol. It's when you want to prove that.
Okay, no, it's not part of the protocol.
So that trusted setup, whatever, is not part of the protocol.
Okay. So the only thing we need for the trusted setup is powers of power. So if we had another way of getting powers of power, we'll go that way. So maybe I should just talk about that question Oba asked some time ago about the trusted setup per circuit and the universal trusted setup. Right? So basically, if you're dealing with polynomials, if you're talking about polynomials and you want to do a trusted setup for a polynomial, right? That trusted setup is universal. You're talking about polynomials, right? So it's universal. So you can do the trusted setup for, let's say, you can do a trusted setup that takes into account a polynomial of degree 1 million, right? Then somebody with a somebody that wants to commit to a polynomial of degree 100 can use that your trusted setup parameter, right? That's your powers of tau. Somebody that wants to commit to a polynomial of degree 50 can use your powers of tau. Somebody that wants to commit to a polynomial of degree 10 can use your powers of tau. So you did one trusted setup, which is universal, and anybody that wants to commit to any polynomial of any degree lesser than the degree of your trusted setup can use that your trusted setup parameter. So that's where the concept of the universal trusted setup comes in. That trusted setup to get those powers of tau is universal, right? So where the trusted setup per circuit comes in is where you want to commit to a particular circuit. So you have a circuit. That circuit may be big, right? You have a GKR circuit. That GKR circuit may be big, right? You don't want to be generating ADI molai for every. You don't want to be generating ADI molai for every layer, right? Because let's say every layer's polynomial can be crazy big, right? So you don't want to generate ADI molai for every layer. So now you will now need to. The trusted setup per circuit basically helps to summarize the circuit, right? So you summarize the circuit and you get a prover key and a verifier key, right? So that prover key and verifier key contains a summary of the circuit. So after generating that prover key and verifier key, you cannot use it for another circuit, because at layer 5 of the new circuit we may have an AND gate as the first gate, and at layer 5 of the old circuit we may have a multiplication gate or a custom gate as the first gate, right? So once we have decided to summarize the circuit, that now brings us, or that now limits that trusted setup, right, to that particular circuit. We are summarizing the circuit and we are generating a prover key and a verifier key. For those people that have written second, even the trusted setup in second, they first do the universal trusted setup, right? They first do the universal one, and then based on that universal one, they then do the per circuit trusted setup, right? So the universal trusted setup can be done once and used multiple times, right? But the trusted setup per circuit is, you can only use it for a particular circuit. If you want to talk about a different circuit, you will need a new trusted setup. So if you may decide to use the powers of tau of the universal to now do different other multiple trusted setup per circuit for different circuits. I don't know if all what I've been saying, if it makes any sense.
Because I understand what you said about different universal planets per circuit, but this one that you just said, I don't get.
Okay. Is everybody following?
Yes. Yeah, follow.
Oba,
That makes sense.
to some extent. Levy. Bilikis. Karima. Jerry. Cass. That's it. Okay, let me just go over it again. Right. So we have a polynomial commitment scheme, right? And we can use that polynomial commitment scheme to commit to a polynomial, right? So when we want to do a trusted setup, the trusted setup is basically to enable us to generate tau, which is a random number, right, that we can use to evaluate a polynomial, right? We are generating random numbers that we can use to evaluate polynomial. That's just the reason for trusted setup. You get. So you can decide to do a trusted setup to generate the powers of tau for a polynomial of degree 500. Right? You generate the powers of tau. Trusted setup to generate powers of tau, right? After you've generated the powers of tau with 500 elements basically for the different powers of tau, right? If you want to commit to a polynomial of degree 5, you can use these powers of tau, right? Just take the first 5 elements, right? Or sorry, the first 6 elements, right? And then you can commit to this polynomial of degree 5. If it's degree 50, you can still use the values of this Trussell setup. Take the first 51 elements and do your dot product. No, it doesn't work for just that univariate.
So, you know that for an element of 500 now, 500 is multilinear. You know
Okay,
that
is it the multilinear case you're talking about? Okay, for the multilinear case, you know we have 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, right? So if we want to commit to a polynomial with 2 variables, so basically need like that's 0 0 0 1 1 0 1 1, right? So one thing we can do is like to blow this guy up, right? We can blow him up to 3 variables by adding plus 0 c also, right? And then when we blow him up, we can do an element twice product, right? Or an element twice, we can do a dot product with him and the Lagrange basis of the powers, like the encrypted Lagrange basis.
that's what I was asking.
So
It's like I wrote the first line.
yeah.
Only what's from here.
So you cannot
Okay,
possibly-
yes, that one just
you
works
cannot
for
possibly
you.
remove
From here. Ah,
can you?
no, you can't.
You have to know what this one do. You can't do that means you can't technically do a universal setup for multilinear. That's circuit. That's you have to use the polynomial to do a setup.
And the
Uh-huh.
number of
You,
Number of you do it.
yeah, the number of, like this, you can still think of this as universal, right?
Yeah.
Just that this person will need to do more work because he will blow up before doing the dot product. For somebody that wants to commit to, yeah, for somebody that wants to just commit to a polynomial of degree 3, can just do like a dot product, right? So this one, somebody with a polynomial of like 1 variable, like 0 and 1, person can still blow it up to 3 by adding, like, if this is A plus 0 B plus 0 C, right? But that's a lot of work, and then doing the dot product.
We still have to do it in our proof.
Yes, you still need to do it in your proof, right? So the Trussell setup we use to generate this value, you can think of it as a universal Trussell setup. Why? Eh?
But that's okay.
No, not for this
You
circuit.
know this one now. You are not doing are you doing the polynomial? You know the polynomial. This I can
The 500.
yes.
The 500 here is the degree of the polynomial. Okay. So it's like based on the degree. We don't even care about the polynomial. The polynomial is not our business. The polynomial can be anything. But yeah, so it's just the powers of tau, right? In the univariate case. So it's just tau we care about. Yeah. So we can do it once and use it to still the same values of tau. We can use it to commit to 3x plus 2. We can use it to commit to 5x squared plus 4x plus 9. We can use it to commit to x to the 1000 plus 4, right? Still, okay, sorry, 100. You get? So it's bounded, right, by the degree, but we can use it to commit to multiple polynomials, right? So that's why it's like a universal process setup. We can do it once and use it multiple times to commit to different variables, to different polynomials. Same thing as the multilinear case, right? After we generate this Lagrange basis, we can use it to commit to polynomials of smaller number of variables, right? So we can think of it as a universal process setup, right? So when we now talk about
So if this is universal, right? This one,
yeah,
and you want to commit to like a 2-degree polynomial. This is too much.
yeah, it's too large, so you blow it up,
You blow up
the
polynomial.
polynomial, yeah, in two variables. So you blow it up and then do the normal dot product. So,
Okay, because at the end of the day, it's going to give us a scalar as a commitment.
yeah,
But then anything that we are doing down the line, we always have to blow it up to meet the
yeah, to meet this number of variables. It's a lot of work, true,
Yes.
but we can use it, right? It's a lot of work, true, but we can use it.
Is that why you said we can use the hours of time like Ethereum generated?
Yes.
So for instance now, let's say they are only use like x to the 1000, so we have to also blow our ourselves.
No, in the univariate case, you don't need to blow it up, right? You can decide to blow it up. But blowing it up is still the same thing as just taking the parts you want in the univariate case. Right? So you can do, if we had x to the 0, x to the 1, x to the 2, x to the 3, x to the 4. Right? And you want to commit to a polynomial 3, 4. You can decide to blow it up, right? 0, 0, 0, and then do a dot product. Or you can just decide to take this guy.
Oh yeah, because multiplications equals 0.
Yes.
But in great case, it's easier.
It's easier.
Yeah.
Makes sense, Abby? Okay. So the thing now is basically this is, you can think of this as a universal process setup. You can think of this other one as a universal process setup, right? Same thing, same way you can think of Ethereum's the process setup they did. Yes.
Was that when you view
Yeah, I think it's univariate. Yes, it's KZG. It's univariate. So that's where we talk about like universal process setup, right? So when we now want to talk of process setup per circuit, we are now involved in a circuit. So we're not talking of a particular circuit, right? So basically a circuit, you can still think of a circuit as a collection of polynomials, right? Your Adai and your Molai basically defines your circuit. Your GKR circuit, your Adai and your Molai defines that circuit, right? So that Adai and Molai can be big, right? It can be crazily big. So you now need a way to you don't want to basically keep track of that big polynomial. The process setup, when we talk of process setup per circuit, that process setup helps us to summarize the circuit. The circuit may be big but we are able to reduce it. We're able to summarize it and then generate a prover key and a verifier key. The prover key will help the prover to generate a valid proof. The verifier key will help the verifier to verify that the circuit was evaluated correctly without needing to know the entirety of the circuit.
There is a question you asked yesterday when I was there. I think just so the question he asked was like, why was I like doing my evaluation, my circuit evaluation inside this new function, right? So let me just for what you're saying. So if you don't do my evaluation inside our group, it's from that circuit that the prover is going to get the other and more and also the people. So if it's outside, that means you have to be passing the other and the more in the proof so that the prover will get the communication.
It depends if your information is stateless, but my implementation is stateless. So if even though you evaluate outside, by default the circuit keeps track of the evaluation.
Yeah, that's the one.
Okay. So the idea of the trusted setup per circuit is to help the prover and the verifier summarize the circuit. Right? So we have the universal trusted setup which helps us to generate tau. Right? And we now have the trusted setup per circuit. So we now have the trusted setup per circuit. That trusted setup per circuit helps us to summarize the circuit. Right? And basically for security, right, since we can basically think of our circuit as polynomials, a collection of polynomials, in order to commit to those polynomials in the circuit, we can decide to evaluate them at tau. Right? So you can think of it as like evaluating the circuit, the polynomials in the circuit at tau, and then committing, like, to commit to it, right? So instead of the prover and the verifier to keep track of the adai and the molai for each layers, like with respect to GKR now, they can just keep track of the commitment to adai and the commitment to molai. Right? That may be like, we're not saying people should implement it, but for the ambitious ones, you get, you can.
Where's the ambitious ones?
Okay, so the thing is, once we evaluate the adai and the molais at, say, tau, right? Once we evaluate the adai and the molais at tau and we have a commitment to them, we cannot use those commitments for a different circuit, right? Because say those commitments are now talking about a particular circuit. So that's where the trusted setup per circuit comes, right? So in that case, we have now talking about a particular circuit. We can't use those parameters generated, which are like the prover key and the verifier key. We can't use them for another circuit, right? So like I said, like those who have worked with second, there's basically like two stages for a growth 16 proof, right? You need to do that universal trusted setup to get your tau, right? And then you do a trusted setup per circuit to get your prover key and your verifier key.
So like just the percentage is like specific to that circuit.
Specific to the circuit. Yeah. So that's the so does the trusted setup per circuit and the universal trusted setup make sense?
Yes.
When you
How?
was a bit distracted at the point when we were talking about 500 this now this 500 this millions different degrees. So
Okay.
I think we're talking about I didn't get what you're talking about.
Okay, like what I was basically trying to say there was that when we do a process setup ceremony to generate our powers of tau, like if we decide to generate the powers of tau up to tau to the 500, right, we can use this tau to the 500 number of, say, elements to evaluate any polynomial of degree less than 500. So any polynomial at all of degree less than or equal to 500, we
That's
can
why
use
you need
it.
that 1,000.
Yes, yeah, it was beyond. So this basically puts a cap to the degree of the polynomial we can commit to.
And once it exceeds that,
They can't go above. Yes. So there's now the transparent setup. There's a process setup, a circuit, there's the universal process setup, and there's the transparent setup.
That was that.
Yes, that's what starts with. What does transparent setup mean? It's transparent, it's like anybody can do it.
So that was start.
Starts. Yes,
I thought start don't need a setup.
they actually do. The setup of is basically picking a hash function. That's just the process. That's the setup. So it's transparent.
If it's transparent, that means anybody knows the tau.
No, you don't need to know. There's no tau in this case now.
So what's the process of setup supposed to generate?
The transparent setup is just picking a hash function. You know, like I talked about earlier, in stocks, we commit to the evaluations of the polynomial.
Which is basically like the polynomial.
Yeah, which is basically the polynomial, right? So in evaluation form. So stacks works over univariate polynomial, right? So we commit to the evaluations of the univariate polynomial. We commit to the evaluations of the univariate polynomial in evaluation form, right? And we use Merkle commitments, right? So picking a hash function for that Merkle commitment is the transparent setup in stack. You can decide to use Poseidon, you can decide to use Pekka, you can decide to use Shakiri, you can decide to use anything, but
is that you go? Oh, the last one.
anything, you can decide to use anything. Okay. Yeah. So picking that picking that hash function is the transparent setup. So you can, like, everybody knows SHA-2. I know that if I hash 0 with SHA-2, I'm going to get EF, JK, IL, MNOP, right? And I don't need to give you the hash function. You can get the hash function anyway. But the hash function, a hash function is a hash function. It's deterministic, right? If we hash the same thing, it should give us the same result. So when we pick the hash function, we can basically now work with it. So in the Merkle in stacks, so we use it to generate our Merkle commitment and also proof generation, like when we want to generate the proof and also when we want to verify. So does that make sense? Like the difference between process setup, like transparent process setup, universal process setup, a circuit. Hope that's clear. Eh? So transparent, there's no, we are not picking, you're not hiding any tau. It's just we are just picking the hash function.
We are speaking the hash function.
Yes. Because our commitment is the Merkle commitment.
Oh, I was seeing it in light of KZG, but that kind of transparent setup cannot be used in KZG. That we are using something like all this
Merkle, yes. Yes. Okay. And
I was thinking about like we're using it in KZG.
yeah.
Look for KZG, we're using the tower and all that.
Yes. So there are, it's not just like there are other protocols. It's not just stacks, right? There are other protocols that use transparent setup, right? So like majorly any protocol
What
that
is
Zcash, Zcash uses IPA. Yes. Have you? Is it IPA or bulletproof? They basically consider them the same.
I know that bulletproof sounds familiar, so I'm sure that
Yeah.
was the question. Sounds really familiar.
So bulletproof and IPA are kind of like similar. IPA, inner product agreement.
No, like I've read it from like
Okay.
okay.
So
This universal is there any particular material?
Yeah, we can hear you now.
I'm asking this one personally. Is there any particular material?
There's no personal conversation.
on the universal process
Peter,
system.
we can't hear you.
Can hear you.
Why is the story Peter? When he was talking, we don't hear him. We don't hear you.
We want to hear you.
Okay, so for the ZKP MOOC course
They're asking
by Dan Bonnet and the ZKP MOOC course.
Yeah.
Yes. So Dan Bonnet did an ex. Huh?
Photography 101.
No, this is a YouTube. Yeah. ZKP MOOC. MOOC. Yes. So Dan Bonnet did like an excellent work. In short, all the tutors is a series close to 15 to 20 videos of like 1 hour to 1 to 2 hours. Like that course will basically get you like will give you like a high level overview of the entire space,
What was it? What was it?
the whole space, the ZK space,
What's the name of it?
ZKP MOOC, the MOOC. On YouTube. Yes. So okay, so like the whole trusted setup, universal setup stuff. Hope it makes sense now. Okay, then bruh, see how we diverted. Crazy. Okay, so we need to be able to commit to a polynomial. We need to be able to open. We need prove. We need verify.
Yeah, it functions for our implementation.
Yes.
For the KZG.
Yeah,
What
for
is your
multilinear KZG. Huh? So open the verifier. You can basically put two of them in the same this thing, right? You can put two of them in the same function. Open is basically evaluate at the points the verifier told you to evaluate at and return a result V.
Okay, so that's open. What is you going to think that one? Okay. This one returns V. Why proof returns the proofs?
Y probe returns the proofs. Right. Then verify is for the verifier takes
Sorry. I'm going to take you back in info.
eh?
I'm going to take you back in info.
No problem.
So open returns V.
Open returns V, yes.
So
But you can as well do it in the proof, right? Where you return the proof and the evaluation.
so for the investor success setup, you say we have now up to account 500. Right?
That's in the univariate case.
No, I'm thinking about it now.
Yeah.
So if we now have, if we want to commit to a multilinear polynomial that is just three variables, that's A, B, C, and then our universal presence setup is like T to the 500. So how do you blow up that? Because what we are having is like 8, like T to the 3. So how do you blow that up to like 500? Or is it not possible to have that T to the 500 because that's the univariate case?
The 2 to the 500. Oh, you
Sorry, I said tau to the 500.
like that would be the tau 1, tau 2 to tau 500.
Is that
So-
univariate case specifically?
No, it's not.
No univariate. So we're running that for multilinear.
Wait,
That's in
the one with this one was the univariate case.
That's the univariate case.
Yes,
That's a universal process setup
for
for univariate
univariate.
specifically.
Yeah.
So what can
For the multilinear,
multilinear
it will be if you have 500 variables, right?
that means going to be 2 to the 500.
That it will be 2 to the 500, the Lagrange basis. Right? You need to generate this Lagrange basis polynomial for the 500 variable.
Okay. So yeah, I'm assuming that there is a process setup already. By those numbers, and then we just have 500 in it. So if I want to commit to that project, that's using that powers of tau generated by that process setup. I'm going to blow up this multilinear polynomial to 2 to the 500.
Yeah. That's a lot, right? That's a lot. Or you can as well do your own process setting. But how can you trust? How can you trust your own process setting? You get
How can we trust their own process?
it's because like you can't even trust it, right? You can't even trust it, but it's kind of like a community thing. Like a lot of people it have been vetted by a lot of people contributed, and like well-known people in the space and people that experienced
Because
people.
like vetted.
Yeah, it's vetted. Ah, good, right? Okay. So, okay, so yeah, we're talking about this guy. So I have the commits, we have
Commit is very settled.
commit comes after the processing. You must have your powers of tau before you can commit. Right. So you must have your powers of tau before you commit. In order to commit, you need the powers of tau, right? Or the Lagrange encrypted Lagrange basis, right? And then you have open, which returns V, right? We have proof, which takes the polynomial and the point the verifier wanted to open at, right? And generates all the quotient polynomials.
verifier side is very good short.
Huh?
The prover side will be short.
Yeah, the prover will be struct. Yeah. You can decide to implement it out, right? It's design decision. Okay.
What is it we prove generate?
The proof. It will give us quotient polynomials or proof, like our quotient polynomials evaluated at the respective tau. That's what our proof give us. So basically give us G1 elements, right? Returns G1 elements. Open will return a field element. Commit to return a G1 element. Verify or return a bool. Right? Okay. So, does everybody technically know what they are expected to do? Eh? You need to take it step by step, poco a poco.
Why does return a G1?
A vector of G1 elements are Q polynomials evaluated at tau. Yeah. Okay. Okay, so okay.
Oh yeah, in
Okay, so like
Guys, all those Q1 blow not evaluated at full time.
so with this, I think we should be good to go, right?
Sorry, Apple. So yeah, this is what was here and the functions.
Yeah, the functions.
Commit, you get the evaluation of the evaluation of
Polynomial at tau.
yes, commitment.
Yeah.
They open at the random point rather.
Yeah.
A
Or open at a vec of random point.
ABC.
Yes. Yeah.
Then you get a field element.
Yeah, you get a field element.
Then the proof, the QA. Did you explain how like the proof is going to give us QA?
Yeah.
QA at
Evaluated at
tau.
tau. Yes, at tau b tau c.
Then QB going to give us tau C.
Yes.
Then QC going to give us
The
constant.
constant.
I'm going to verify that those are the equal.
Yes. Which is a verified function.
So these are oversight.
No, this is the entire protocol.
So these entire.
Yeah.
Okay. It's not that. It should not be that.
That commit is the
Have
of
it?
tau.
Eh? The commit.
Yeah.
It's
That's
proof
of
not
tau.
supposed to be.
Yes. This G1, this f of tau.
Why? This is the point.
Yeah, it's a point in G1.
How is it a point? Because we're
It's a
saying
full
f-
evaluation of the
We're saying
polynomial.
f of tau minus v. V is a scalar.
No, the commitment. We are not subtracting v from the commitment.
So if now we're raising, we are going to convert v to be in like a point.
Yeah.
Yes.
The example we treated, I think 2 days ago. Is there any modification? Like I understood the way we did the thing. If I go that route, will I no modification?
No.
So
Eh?
it's going to
The example we did in class.
I see you're
Okay,
going
you
to minus
understand
B
that.
again.
Eh?
You say you're going to minus B.
No, like the commitment itself.
Yes.
We're not subtracting B from the commitment.
Okay.
So the commitment is just F of tau.
Okay. Okay, I just need to get the QA. I
Yeah.
think the minus of the commitment of the B to get the QA.
Yes, to get the proof.
To get the question.
Yeah. Makes sense, right?
Yeah.
Okay.
Yes. I'm sorry, I think I'm in the last video, I think minus 2 from the commitment to equate to
Now that's when the verifier wants to do the verifier's check.
eventually.
Yes.
Just-
But the initial commitment that the prover sends to the verifier, he doesn't subtract tau. Yeah. Makes sense, right?
Yeah.
Does anybody have any question with respect to this? Hmm? Any question with respect to this? No. What? The mathematics.
Group elliptical. And
You don't even need like these black boxes now. Like APOX have implemented all these things. So, yeah. You don't need maths, but you need English.
He didn't work.
Nice one.
Everybody needs.
At
Please,
least
please,
it's
please.
nice to see that I'm not the only one that received banter.
Please.
They need to be comfortable.
No, like
We say English like pseudocodes like.
yes, exactly. So like basically the same way you say it, right? It should be just similar to that. Since you're taking these functions as black boxes, you get it. So it's more of exactly like pseudocode. I think, yeah, that's. But since you're taking the function, it's not like you're implementing the elliptic curve, right? So like those ones have been implemented by APOX. You get. So it's just like if you understand the pseudocode, like what you're supposed to do, then it's pretty straightforward. But if you're asking for the maths, like maybe the technical, oh, unless you want to go into the weeds, right? That would be like more maths manual. Huh? Ellipticals, yeah, ellipticals, then rescues book, by linear pairing, yes, then,
On top of what you're saying, and I feel just to get what is going on here, no matter the too extreme.
yeah, they may be too extreme, right?
Rest is ethical addition and binary pairing
Should be good enough, right? Okay.
no matter the two.
Yeah. So that's why I said into the weeds.
Yeah,
Yes, the rescues.
so just like the chapters on ethical addition and binary.
Yeah, so like into the weeds is more maths,
They want to
or into the dark forest. Yeah, the dark forest is actually a place on the blockchain.
Semantical.
The dark forest.
Yeah, into the dark forest.
Into
Like
the
it's
dark-
an article.
Yeah, it's
Yeah,
an
I've
article.
read
There's also a game now.
But it's talking about like
There's that for
Talking about me.
yeah, MEV.
terrorist.
MEV.
Terrorist.
Okay, so
The value is the G2 returns. It's not even the same as the value of the G1 return.
yeah, there are different yeah, like different groups, different generators, different number of elements
It's
basically.
terrible plan.
Like I think G1 is, should I say, the base. G2 is a degree 2 extension. Then G12, I think G12 is a degree 12 extension. So it's crazy.
In Apple.
GT.
Is
Yeah?
in Apple.
Yeah, in APOS. Basically, like, not just in APOS, if you want to implement bilinear pairings. The G1, I think, is usually the base group. G2 is usually a degree 2 extension of that. Then GT, for BLS 12381, is a degree, I think, a degree 12 extension. So that's like fields and field extensions. Yeah.
Then how about that? Did you check into that? Although that one is passed out, I don't want to. I think that one is passed out. I don't want to disrupt moving your heart. The one that I was talking about yesterday.
I ran it and it worked fine.
And this guy, we ran it more, so I it's
You guys that must have done something wrong.
definitely more. It's knowing what we did wrong.
Okay, so hope this is clear up to this point. Process setup, all this makes sense, right? I wanted to talk a bit about our arithmetization, but maybe we'll leave that one for another day. Or maybe I will leave that one for another day. Like arithmetization, like R1CS, longfish arithmetization, algebraic intermediate representation. So those are like the three major types of arithmetization, although there's a fourth one, this CCS. Yeah. So all those are just like different ways of representing like a high level language, converting it to polynomials basically. So you convert it to a circuit, convert that circuit to polynomials. Yeah. Based on the constraints in the circuit. But let's not. But still, we are going to talk about it, but maybe not today. Okay, so I think with this, if we don't have any other question, we can
Control the personal question.
call it a day. Any questions?
Good question. No.
Please tell me you were recording. Thank you. God bless you.